Welcome, everyone. Thank you for joining us for today's webinar, Fire and Gas Best Practices, presented by Hassan Mobashar and Rebecca Fritz. Hassan is a process safety principal engineer who works out of our Canada office, and Rebecca is a process safety senior consultant at our Houston location. Our BakerRisk presenters are uniquely qualified to address this topic today, combining deep technical expertise with extensive hands-on experience supporting operating facilities, capital projects, and regulatory engagements globally. Their work spans consequence modeling, F&G, and SIS design and verification, QRA, and incident investigation, allowing the discussion to be grounded not only in best practice, but in what is proven effective in real facilities, under real operating conditions, and in front of regulators and stakeholders. Now, I want to go over a few housekeeping items. Please type questions into the Q&A box in the Zoom control panel, and our technical staff will respond to the questions. I want to say thank you to Annette and Rachel for being here with us today, along with Murtaza, to answer those questions in the Q&A chat. Finally, at the close of our webinar, please provide feedback by responding to our survey. We're excited to have Hassan and Rebecca present today, so without further ado, I will turn the time over to our presenters.
Thanks a lot, Naomi. Good morning, good evening, good afternoon, everyone. Thanks to attending our Fire and Gas Best Practice webinar from BakerRisk. This is Hassan, and then we have my colleague Rebecca. We will take you through the best practices and then how we do F&Gs in BakerRisk. A little bit about me. I'm a principal engineer in BakerRisk. Before joining BakerRisk, I worked in Chevron upstream and downstream for 19 plus years. Including overseas location in Thailand and China's both onshore and offshore plants. And then I'm going to the next slides where Rebecca can give her intro. Rebecca.
Hello, everyone. I'm a Senior 1 consultant here at BakerRisk, and I've worked here since 2018, supporting mostly facility siting study, QRAs, fire and gas detection, toxic shelter testing, and accident investigations.
Perfect. Thanks a lot, Rebecca. So we're going to go through BakerRisk overview and introduction to F&G. Before we get there, just wanted to give you a little bit of BakerRisk overviews. We are located all over in the world. It's 100% employee-owned companies, 42 plus years in business, 200 plus employees, and 135 engineers and scientists. We have various project locations in the world. We have our headquarters in San Antonio, but we have a pretty decent setup in Houston office, Los Angeles, Chicago, Philadelphia, and then overall Canada. We have operations in Toronto area as well as Calgary area. We do have offices in Europe as well as Egypt, where we focus on the European and Egyptian areas for our service. So the webinar agenda, we want to talk a little bit about how we're going to go through this specific topics. We're going to talk about introduction and background on the F&G's one importance. I will present that. I will talk a little bit about challenges with detection mapping and evolution of standards. Rebecca will talk about BakerRisk methods. Then I will talk about performance criteria, mitigation and action. Rebecca will then take us through a case study that we have done earlier, and then we will have concluding remarks, and then we will try to answer any of the questions that you ask. So why F&G is important, and then what is F&Gs? So a little bit of introduction. Before we do that, just wanted to let you know our services areas in F&Gs, fire and gas systems. We do provide F&G layout development and resulting coverage of detections. We provide philosophy for clients coming in with us to look into their plans, look into their equipment, and develop F&G philosophy document for them. We obviously do consequence modeling and facility siting studies, which is the core of fire and gas sensing devices placement. We also do coverage assessment for existing layout, and then provide client that whether their layout coverage is adequate. We do risk-based modeling in terms of QRA, and then we also do fire hazard and mitigation analysis, FHMA. So you may want to ask, what is fire and gas system, FGS? So fire and gas systems is comprised of mainly three items or three uh, areas that if you want to focus on. The first one is detections, the second one is decisions, and the third one is actions. So the detections is comprised of sensors technologies. Decisions take place in process control or logic solver where the signal has been processed, and action is based on how you set up your fire and gas systems to act upon. So FNG systems does not itself reduce risk, it detects, but it needs to interface with other systems to measure and mitigate risk. For example, it needs to work either with the operations, so the operations can shut off a valve, open a valve, or it would work with an automated system where it would open a deluge system, or it would depressurize, or it will shut off a system to stop feed coming in. So you might want to ask, so if it doesn't do anything by itself, why implement FNG? The main answer is that it provides early reliable awareness for abnormal condition. And if we know the abnormal condition before, we can definitely take action and reduce the severity of escalation and consequences. And also FNG system can provide automated actions based on the programming that has been done in the back end for the logic solver to provide automated actions, either to shut off a valve, open a deluge valve, or provide annunciation for operations to take an action. For example, divert a flow, close a valve, open a valve, or provide emergency response guidance for employees and personnel in the plant. So in general, detection can notify release unseen by human because human, we have limitation in hearing, listening, seeing, but detections can be various, and then it can detect very small leak. It can detect very fire that we cannot see in our eyes, and then provide early annunciations. So in terms of the response planning, detection is the first phase where we provide either detections and then either point line or fire detections. Eventually, it gets to the response where we have alarm, protection in terms of emergency services, stabilization in terms of isolation, depressurization, firefighting, personal recovery, maybe master shelter in place, medical, and then eventually plant recovery, startup and operation. So in the next slide, we will show you a little bit about what kind of software we use. So over here, what you see in our WEBTF testing facilities where we are testing a horizontal release of propane. And we have this FNG tool software that we use extensively in BakerRisk, which is a very powerful software. And we use this software to detect a toxic or flammable gas release using ISA 84 methods. And then we provide a defensible layout based on the dispersion clouds or the heat released that's coming out if there is a fire. There is a link provided here for the software. After the webinar, we will share the slides. So feel free to go in, take the link, and then familiar yourself with the software. This is a pretty unique software and has a lot of capability. So challenges with the detection mapping. So we're going to talk a little bit about what are the challenges with detection mapping, and then we will talk a little bit about the standard that came out because of the challenges. So in terms of challenges with the detections, when a gas is released, it varies in locations. It depends on the size, depends on the flow rate, depends on the dispersion and momentum, phase, duration. It can be various. So what happened previously in the history that people didn't know how to place detector because they could not model the gas release properly. So there were inconsistent and sometimes non-defensible coverage. When the gas is released in an open field, that's a different pattern. But when the gas is released in a plant environment where you have congestions, elevation changes, and ventilation pattern, it gets very unique, and then it's difficult to predict and difficult to detect the gas. You can say that you could have a lot of detectors, and then you could increase the detector layout. But if you don't do that based on a proper dispersion modeling, if you don't know where the gas is actually going, then you could increase the detector, but it will not give you proper coverage. And eventually, what it will give you a higher maintenance. It might provide nuisance alarm. On my left side, what you can see is that various development of standards starting from early 1850s, where flame safety lamps was introduced. At one point, they used canaries in a coal mine for toxic presences. And eventually, as you go in, you can see that the detector has been, the standards has been developed from more of a prescriptive-based, experience-based to a more performance-based, calculation-based. So over here, I just put few standards here, but there are multiple other standards. But these are the standards. They are the core. 1993, UK HSC OTO 93s. They had empirical relationships, and then they provide data that 60% of the release is undetected. In 2016, ISA or BS 60079 came in, and then it provide guidance on uncertainty and how to address. In the heart of our detection methods that we work with, the ISA 84 TR07, it's reframe the detection placement, and then it's provide approaches where you can put detector as a performance base rather than a perspective one. And then later on, BS 60080 came in, which provides practical guidance on software-based tools. Right. So you may want to ask, what are we trying to detect? How do we detect? So the request to add detection comes from various sources. It could be a hazard that they have done where they have provided recommendations to install gas detections. It could be a previous incident that happened, and then the plant may need detections. It could also be an insurance survey. Many insurance survey, they would wanted a fire protection philosophy as well as a gas detection philosophy, as well as fire and gas systems in their plants. In terms of defining the scopes, the things that we look into area to cover. Is it a single scenario, single unit, or entire plant? Are we talking about indoor or outdoor? Are we including buildings? What are we trying to detect? Is that a flammable gas? Is that a toxic gas, or both? Are we also trying to detect fire? Are we trying to detect smoke? Or are we trying to detect lack of oxygen or presence of toxic material that people cannot breathe, right? So the evaluation basis starts from how will you know that are adequate detections, and then is the basis for developing FNG philosophy document or ADAPT standards. On my right side, I kind of provide a little bit of example of fire detectors, flame eyes that we see in the plant, heat detectors. Product of combustion is smoke and carbon dioxide. This is very common to see in the house of residential areas. Obviously, we know about gas detector that you can install, which can provide detections of flammable, toxic, as well as provide detection about lack of O2. Rebecca.
Yes. So now we're going to talk a little bit about where to actually place these fire and gas detectors. Next slide. So there's a few generic ways to, calculate your coverage. So one of them is the geographic base. And this is typically when you're looking at a uniform structure, it's easy to implement. And you're really just looking at what is the general area of where my hazards are at. Some key drawbacks is that it can be costly. It doesn't consider the likelihood of releases, and it can lead to some overcoverage and some undercoverage, depending on if it's a high risk or low risk area. On the other side, there's scenario based. So instead of looking at an entire area saying that there is flammables or toxics that can occur, we're looking at a scenario by scenario basis to say, here's the exact equipment that's going to have the release, et cetera. So some key advantages to this is it's very specific to the hazard and to the location, and it places detectors where they're most needed, and it does allow for optimization. Some drawbacks to the scenario-based methodology is that it needs consequence modeling, so it requires a little bit more upfront modeling, and then it's really focused on those high-risk releases, so lower likelihood leaks may go undetected. So this is a very generic laydown of our methodology, but the first thing is to define the scenarios that you're trying to cover. As Hassan was saying, are we looking at just a single scenario, a single unit, or are we looking at the entire facility? And typically a facility siting study or other studies can identify those different hazards to identify. Then you have to go through the consequence modeling, so modeling them according to local weather data, their process conditions, and then with a special look onto releases inside of enclosed structures, those can be greatly impacted by the wall configuration and ventilation system. And so in those cases, even more detailed consequence modeling needs to occur. And then the final step of the methodology that we use here at BakerRisk is to, what kind of coverage are we looking for? So sometimes that is set by our client's internal guidance or adoption of some kind of standard. But in lieu of both of those, we use typically the ISA TR 84 that was released in 2018 that helps define the scenario-based target coverages for each piece of equipment. So here's two different ways to look at some dispersion contours. So on the left-hand side, we have a composite dispersion contour. So that's showing the release from a piece of equipment going in all directions. So it kind of develops a sphere or, a different area of where different gases could accumulate. On the right-hand side, we have an individual direction dispersion contour. And so that's just showing one release from one direction. So if you can imagine rotating the right one around in a circle, you would get the composite one on the left-hand side. So you can use these composite contours for geographic coverage, by developing that volume sphere and saying, okay, I want to detect stuff within the orange circle here on the map. It also helps you to identify where different places of gas could accumulate. But if we were looking at the scenario-based coverage, then we typically look at that individual direction contour. Alternatively, looking at jet and pool fires. So there's two different ways that we look at this. So there's the thermal radiation. So that's, what kind of radiation you're getting at different distances. And again, that's shown as the composite contour. And then there's also the actual flame cone. So when we model it here at BakerRisk, we're looking at a tilted cylinder for the fire flame modeling. And so again, you can use these composite contours to look at different things. A lot of times looking at, mitigation planning and where would water spray be effective and like what kind of equipment is being impacted by this thermal radiation during a fire event. So detectors are placed with many considerations. The likely release point, the momentum, where it can accumulate in a gas area, the dominant wind direction, and you want to make sure it's clear of obstructions. Luckily, with our proprietary software Fire and Gas tool, we can model many different detector layouts, one after another. So we can put a layout of detectors there, see what kind of results it's getting, and then if it doesn't work, we can try a different layout, or we can start paring down the number of detectors to make sure we're fully optimized. Because as Hassan mentioned earlier, if you place lots and lots of detectors, it causes usually nuisance alarms, a maintenance burden, et cetera. So really making sure that you have enough detectors, but not too many detectors is really important. So that's what the benefit of the software can do for you. So here's an IR video, so kind of showing I think that same propane release that Hassan showed earlier. And really, this is just showing that we are doing research to constantly make sure we're at the forefront of what's available. So we've worked with numerous detector companies to understand the detector response time, the reliability of detectors, et cetera. And we've also run two major internal research programs to answer these questions with real world data.
Perfect. Thank you so much, Rebecca. So now you have seen how we test our software because of our testing sites in various locations. We also have seen a little bit of our software that Rebecca talked about, how we see performance based on our fire and gas tools, the shape of the flame, the shape of the contour of the dispersion that coming in. You have a basic ideas. So we're going to talk a little bit about performance criteria, mitigation, and action. So we talked earlier that, okay, so detector doesn't do anything by itself, right? So it needs to work with something. So we're going to talk a little bit about that in the next slides. So this is called fire and gas system safety availability. This is a calculation approach we are familiar with using IEC 61511 or other reliability calculation method to perform the actions of a certain detections, logic solver, as well as final control element, for example, a deluge valve. So the heart of the calculation is the probability failure um, um, of demand in average, which provides the core metrics of the likelihood of the system fails when there's a fire or gas event occur. So we need to calculate the PFD average for sensors, logic solvers, final control element, and then definitely needs to talk about how the sensors are placed in terms of a voting regime. Is it a 1 out of 2, 2 out of 3, or something like that? And we provide reliability calculation based on the configurations to find out PFD average. So FGS effectiveness become the detection coverage, safety availability multiplied by the mitigation action effectiveness. So FNG will not do itself anything, but it will interface with the final control element as well as the logic solver as well as the operator to mitigate the risk. So you might want to ask, what is the effectiveness of a FGS action? So it measures how well a system reduces the severity of hazard. For example, fire gas leaks after they occur. So it's a mitigative measures and how it's interfaced with either automatic devices like shutdown valves or deluge valve, or how it interact with the operations. So in terms of mitigation action effectiveness reflects the confidence in the FGS ability to reduce hazard severity post-detections and then depends on three factors: timeliness of the activations, human factors, and hazard severity. So you may want to ask, once we detect, and then we talked about the emergency response plan, how it chronologically goes from detections to activations to response and mitigation. So over here in the picture on the left side, you can see some detectors for areas. And then on the right side, you can see that, detector for an air intake chimney or air intake stack present. So once the detection has been generated an alarm or activate a device, so you may want to ask, what do we do? Do we just stay there, or do we go somewhere, or do we provide emergency response, or so what are the steps, right? So that is a key questions where you might want to ask that, what if we have a shelter in place? Can we go there? And then if that shelter in place is good enough to provide your protection, right? So this is something that important that is connected heavily with the detection system as well. So I'm going to give you an example of a shelter in place. This is called Fortress Multi-Resistance Building, or MRB. This is designed by BakerRisk. This is a multi-hazard building, and then it provides protections from flammable gas, toxic gas, fire, and explosions. So once a detector detects certain amount of gas concentration, it might provide an alarm, and then for essential personnel can go inside the fortress building and then take refuge in that area. The fortress has monitoring systems which provides occupants what's the condition of outside plant. Also, it provides critical information for units that have been depressurized, shut down, and then if there are any kind of toxic and flammable gas present in that unit. Also, some of the Fortress features give you customized graphical user interface, which displays the indoor situations in terms of any kind of toxic gas presence. Some of the Fortress, they also have self-contained breathing gas providing, and then the system is designed for high reliability exceeding 99%. Back to Rebecca.
So yes, so now that we've talked about, that you need to develop a fire and gas philosophy document, you need to define your scope. Well, what do you do after that fire and gas detection? So this will walk through a little bit of a case study. So here's a figure that we've made to model this case study. So we're saying that we have a, half-inch jet fire from a seal leak from the suction of the propane pump. And we're putting it pretty close to that propane storage that is feeding that pump. So here's a couple different things that we're going to be talking about later. We have our fire detector, and then we have our cone detector. So that's that pinkish red, triangle that's representing that fire cone that the detector sees the fire. And then we also, on the blue on the left-hand side, we have a deluge model. So, something that would start putting water on that propane storage tank. So we're going to go through a few different cases. So this is case one. Case one, we're saying, is going to be a manual and visual only fire detection. So we're not going to say that fire detector's there and there's no deluge there. So we have a half-inch fire from that propane pump. The flame is probably impinging or close to impinging on that storage vessel. There's no fire and gas detection. And so we're saying that the response is delayed by 10 minutes before that fire is visually discovered. And then what we're going to be using as kind of a set time throughout the entirety of these three cases that we're looking at is that time for emergency response to arrive and start effectively fighting that fire. We're putting it 20 minutes. So that effective response includes, getting the fire truck ready, transporting to the scene, getting the water set up, and all the fire trucks and the water spray set up. So this is case one. So we have that response delayed 10 minutes plus that time for emergency response to arrive. And so here's kind of shown on a timeline scale. So we have that flammable release that ignites and detection of the fire to the report of that fire. That's that 10 minutes that we're saying for case one. And then we're saying, 1 minute to kind of go from somebody seeing it to actually telling other people. And so then that dispatch of the emergency response team getting to the scene, we're calling 10 minutes, and then the actual 10 minutes to respond to that fire to actually set up and start the firefight. So if we look at all that time, added together, we're looking at about 31 minutes before we're effectively fighting that fire. Next slide. All right. So case two, we're going to add in a little bit more. So we're going to say that we do have that fire detector, but it's not going to be linked to anything. So as Hassan is mentioning throughout this, detection is great, but you also need to be doing something. So this is that middle state where we have detection, but it's not tied to anything automatic. So we're looking at the same fire. It's potentially impinging on that nearby storage vessel, but we're saying that that fire detector sees it and it's detecting it within 1 minute. So it was 10 minutes in case one. Now it's 1 minute. And again, that kind of standard time for emergency response to effectively respond to the fire. All right, so it's the same graphic, but now we've shortened that first little bit of time. So that flammable release ignites and detects the fire, and then it reports it. So it tells, the control board alarms, or it just alarms outside, 1 minute. And so now we have only that 1 minute plus the 20 minutes for the ERT. So that makes a total time of 21 minutes. Now, I'm sure based on the picture, everyone can guess what case three is. So now we're saying we have our fire detector, but we're going to have our fire detector linked to that automatic deluge. So we're actually going to get water going on to that vessel very quickly. So again, we have our half-inch seal leak fire from the propane suction side of the pump. It's potentially impinging. The fire detector sees it within 1 minute, and then that fire detector, through a logic system, tells that deluge to turn on and start getting water on the fire. So now we have two kind of timelines that are working concurrently here. Again, we have that 1 minute to see the fire via the fire detector, and then that deluge is turning on in 1 minute. So for the deluge, that total time is 2 minutes to start getting some water on the scene, but we still have that manual piece of getting the ERT people to the scene in that 21 minutes. So we have some amount of firefight happening, but we still have the whole cavalry coming on that manual piece. So we have a 2-minute timeline and a 21-minute timeline.
Perfect.
So some conclusion.
Very,
Oh,
very good, Rebecca. Thanks a lot for the case studies. That's actually amazing. This is amazing that you show that how the detection works, both in terms of manual as well as automated. Yeah, perfect. Thank you so much.
yeah. So here we're just kind of going through some high level conclusions. The future of fire and gas detection is really evolving. It's relying less on those traditional methods of saying, oh, well, this is a good place and this is where we placed it at other places. And it's really looking more at the utilizing software to help us. We have a few kind of figures on this side that's showing some different fires that are occurring. And the bottom is a dispersion cloud, but the top one is kind of showing that enclosed fire in a building or some other sort, and just how that will be much different than if we were to have that fire out in the open field or in a refinery. So using a CFD, so computational fluid dynamics, and the 3D gas dispersion modeling is going to continue to play a crucial role in designing these detection layouts and basing it on empirical data. And so another thing that we've looked at is wireless gas detection. So instead of having it run with conduit throughout your whole facility, actually having wireless will help enhance flexibility in the coverage. So if you want to place it in one place and then maybe something else is happening or changing at your facility, it's much easier to move a wireless gas detector than to rerun conduit lines to wherever the new location is at that fixed detector system. Another thing that's becoming more popular is camera-based detection systems. So it's actually a camera that may be able to see the fire and move itself around. This can be very effective in seeing small leaks, maybe before they would get to a detector, maybe that camera is able to see them. And they can also be effective in the response to know exactly where that fire originated at, to be able to direct your ERT team to respond to it, instead of just going to the fire scene and not knowing exactly where that fire started. And then a critical early step in any fire and gas design project is a clear performance criteria. So making sure that you have that philosophy developed and approved by everybody that's of interest to it, before you just start placing detectors, not based on any kind of established procedure. And then long-term reliability of any fire and gas system really depends on regular calibration maintenance, and then also self-diagnosing any issues with those detectors.
Perfect. Thank you so much, Rebecca. I think the concluding comment that I would like to say, like initially, it was very much on prescriptive based. With the development of new software tool and standards, for example, ISA 84, it's becoming more performance based. And many cases where the geometry is complex, for example, indoor, there are options for using CFDs capabilities that we have. Some of the example that Rebecca mentioned, you see on my right side. One is a fire, another one is a gas dispersions. And obviously, the heart of FGS system is the philosophy. So if the philosophy is defined properly, is defensible based on scientific method, that gives you a lot of coverage. And once we install the detectors, the logic solvers, and the valves, we need to function test them periodically to keep the system dependable, and then making sure that when the systems are demanded, they are working properly. Thanks so much, Rebecca. And I believe this is the last slide that we have, Naomi. So I think we're gonna go to the Q&A in the next slide.
Absolutely. And thank you to our audience. You all have been very engaging, and keep those questions coming in. I'm going to go ahead and bring up some of the questions that did come up during the presentation. So first question, where do you see organizations over-investing or under-investing in F&G systems? And how should leaders think about F&G from a risk value perspective rather than a compliance exercise?
Do you want me to take that one, Hassan, or do you have
Sure,
some thoughts?
go ahead. Yeah, absolutely.
I would say getting, that fire and gas philosophy really vetted and make sure everyone has bought in on that fire and gas philosophy document will really help, longer term in the actual implementation stages of it. So making sure that you have operations support at that point before you spend a bunch of money, buying detectors and placing them out there, making sure you have a methodology set to say, where are we going to put it? What are we trying to accomplish? Because just putting detectors out there without thinking through the why or the how really is going to drive up that cost versus thinking about, adding that little bit of time to think about it and make a plan early in the project process.
Yeah, that's perfect. So FGS systems helps really well when there is a philosophy, there is a science and engineering behind it. If there is none, then no matter how many detectors we install, it's not going to help you. It's not going to give you provide coverage, right? It's going to eventually do a nuisance alarm, and then it's going to be a maintenance nightmare. So definitely not overinvest, not invest, but invest based on a performance target, invest based on a proper science and engineering.
Thank y'all for that. The next question is how should F&G strategy evolve as companies move into hydrogen, ammonia, and CCUS projects with different hazard profiles? Do you have any insight on that?
Yeah. So as Rebecca, if I may take that, and then please add on after this as well as you see fit. So as we are moving more towards renewable energy like hydrogen, moving towards like how we capture carbon. And then the plants are evolving, so does the hazard, right? So in terms of previously what we have seen in oil and gas plants or fertilizer plants, we are very familiar with hydrocarbon dispersion, hydrocarbon fire. But hydrogen itself, as well as carbon dioxide itself, they have unique challenges in terms of dispersions, in terms of detections, in terms of sensing methodologies. So as these technologies, move towards further, it requires better procedure. It requires better software. It requires better performance-based detector placement for stronger alignment between the detections, isolations, and emergency response.
Yeah, another thing I'll add on to that one is, maybe when you're looking at a typical refinery or hydrocarbon-based facility, you're able to say, I don't really need it there. It's kind of covered over here because there's a lot of cross sensitivity in the detectors because you're all kind of based around that carbon, baseline. Where if you look at the hydrogen, the ammonia, those almost are always requiring a specific detector for hydrogen, a specific detector for ammonia. There's less cross sensitivity over there. And then you're also going to have to consider the fact that you can't see a hydrogen fire. So maybe on a typical refinery or a hydrocarbon based facility, you're saying, okay, well, I don't need a fire detector there because it's right outside the control room. I'll just see it. Where if that's a hydrogen fire right outside the control room, you're probably not going to see it. There's a couple instances in investigation or in incidents that have happened where someone walked right into a hydrogen fire because they didn't see it. So just having to think about all those differences, as Hassan said, with the different materials you're actually looking at is really important.
Nice.
Perfect.
No, yeah, that makes perfect sense. Another question was, from an operations standpoint, what practical issues most often degrade F&G performance after startup, whether that's maintenance practices, bypass management, or operational changes?
Yeah, I can take a first stab on that. Based on my operational experience in varieties of locations, what I have seen the most common degrader of performance is poor maintenance practice. So many times we install detectors, we have connected them with alarms, we also have connected them with deluge valve, but sometimes we don't do function testing. If we don't do periodical function testing, those devices, when demanded, may not work, and then that creates a problem with the escalation at the plant, and then that create the whole risk tolerance criteria of the plant, right? Initially during design, maybe we have taken that into consideration, and the risk is tolerable. But if we don't maintain them properly, then the risk is there, and it's not tolerable anymore. One of the other problem that I have seen that during any change of equipment, during any change of, let's for example, adding a new unit or adding any equipment, sometimes we add it, but we don't manage documentation. Maybe by adding an equipment, we obstruct a flame eye or flame scanner. Now that flame scanner, what Rebecca was telling earlier, maybe was looking into a propane release from a pump, but now it's obstructed, cannot see anything. So that's something that is another thing that as the plant grows from a one plant to another plant, through significant changes, these things needs to be incorporated. And as the plant grows, the fire and gas philosophies as well as the fire and gas performance criteria needs to grow as well.
Yeah, I'll add just one thing onto that. If you're thinking about, what operations is doing with that information, if there's constantly having problems with one of their detectors, it constantly gives a nuisance alarm, so that to the point where anytime that it alarms, people just hit the ignore button, or, maybe aren't fast enough to go, and they're not motivated to go see it because it's always been a nuisance alarm. It just takes that one time for it to not be a nuisance alarm, to cause many issues. So just staying on top of that maintenance program and staying on top of, if it is a problem with the detector, go back to whoever made it, go back to the manufacturer and say, this is a problem. All the others are working, but not this one. And I would imagine that they would help work with you and send you another one, or, maybe, there's something else going on in that area that needs to be addressed.
Yeah, that's very true. And don't just decommissioning because just it gives you a nuisance alarm, right? Try to understand why it's been giving you a nuisance alarm, because that detector is there for a reason. Thanks, Rebecca.
Yeah. No, and thank you for bringing that up. That actually gets us to our next question. How can sites reduce those nuisance alarms without compromising detector coverage or response effectiveness? I know you'll touch base on that a little bit, but
Yeah, Rebecca can take that if you would like.
I hate to bring this up again, but it goes back to making sure that you have a good layout, right? It goes back to saying, don't put 1,000 detectors into your facility because you're wanting to catch everything. That's just going to cause problems later on. So really making sure that when you place those detectors, you have a reason you're trying to catch something specific, and then make sure it's optimized. You don't want two detectors 5 feet apart and then have a whole gap somewhere else where there's no detectors for 20 feet. So really paying attention to that layout and really making sure it's optimized, not only from a coverage standpoint, but also from a, usability standpoint, as well. So in terms of reducing it, is really to make sure you're not having too many detectors. Obviously, more detectors is probably helpful, but there's that sweet spot where enough detectors are there.
Very, very good. And then many clients come to us and they ask, they have installed this line of sight detector, for example, and then it just provides nuisance alarms. So they do a decommission, and then we work with them and then making sure that, before they decommission, there are proper reason for it. And then sometimes field visit is very important. And then me, my colleague Rebecca, and then a few of other colleagues, we go do field visit and then get accurate data that why some detectors is giving you nuisance alarm, and then provide justification that this may be giving some nuisance alarm for this reason. And then provide actual scientific and engineering background that this layout maybe has been changed or detector has been blocked, and provide solutions for the actually decommission that system.
Nice, making sure that the areas are covered correctly. I love it. Another question that came in was, what role should operations play in validating detector placement and response assumptions made during the design phase?
I would say getting operations involved early is always key. There may be certain areas where they would really appreciate detection. Maybe they're constantly having to go up to this, this problem area of the facility, and it would be really helpful if they just had a detector up there. That's something that they can give feedback on. And then also in terms of almost talking to your maintenance team as well to say, if we have this many detectors in the unit, is it putting them at a similar accessibility? Maybe that's building a platform to get up to the detector, or kind of making sure all the detectors are the same technology so they're not having to switch equipment to do the maintenance. Because if you have, 75% of your unit or whatever your area is on one detector, and it requires this type of calibration or this type of equipment that you need, and then there's 3 or 4 detectors that are a different one, those might end up getting missed. So you want to make sure that you're doing your research to make sure that the detectors that you're getting are going to be helpful, making sure they're going to be in places that operations and or maintenance are wanting in that area. And then also just, making sure that you kind of keep consistent on that so that, you lower any burdens on any of your employees.
Very good. Perfect. Don't want to install a detector that out of reach from a regular maintenance as well as, bring operations um, preference, their experience during the design process. Thanks a lot, Rebecca.
Yeah, taking that proactive approach can, I'm sure, save a ton of money in the long run as well. So, Hassan and Rebecca, it looks like we've only covered a few of the questions that were asked. To our attendees, if you have additional ones, type those into the Q&A box. I am going to ask one more before we conclude the webinar. Hassan and Rebecca, based on your experience, what operational lessons learned are most often missed in F&G design reviews and even PHAs?
I think my experience sometimes when you do a HAZOP, specifically and LOPA, we take credit for FNGs, either a flame eyes or a gas detection system as providing you a restriction factor of 10. Without understanding that when we provide that restriction factor, we need to go back and then take a look into actual effectiveness. Remember that slide when you say that safety availability. Detector doesn't do anything for you, right? So it needs to work with either an operator or a control valve or a deluge system to provide you that coverage. So when you take that credit in a LOPA or a HAZOP, make sure that you have that specific safeguards. For example, this detection system, you provide that calculations, making sure that that detector have the safety availability, that detector has the proper coverage factor, that detector has the proper effectiveness to have that actual being credited in the risk study. So that's my 2 cents.
Yeah, I'll only add one thing is that if you're going to take credit for that detector, make sure it's actually there. I don't know how many layouts I've gotten to say, oh yeah, we have this many detectors, here's all the location, and I go outside and 3 or 4 of them aren't there, or maybe it was they were planned to be there. Maybe they got removed because they were broken, but you know, making sure that they're actually there is probably one of the major things I've seen going outside in the field.
Oh, that's great advice. Well, thank you, everyone. It looks like we've, again, only covered a few of the questions that were asked today. And thank you to Annette, Murtaza, and Rachel for answering those questions in the chat. If you have additional questions, be sure to type those in the Q&A box. Our presenters will answer those questions and will send out and post their responses via email and on our newsletter. We'll also post that on LinkedIn and also to our BakerRisk website. We will provide the recorded webinar, slides from this presentation, the F&G best practice document to reference to, and the answered questions from our presenters. We, again, thank you for joining us. Thank you, Hassan and Rebecca. Great insight, great knowledge. So our next webinar is going to be Building Safer, Smarter Industries, Why PSM is a Strategic Investment. That'll be presented by Teresa Lewis and Michael Metcalf-Smith on February 24th. So again, thank you, everyone. Appreciate your time and efforts. Have a great day.
Thank you, everyone. Thanks a lot, Rebecca. Thanks a lot, Naomi.
Yes, have a good one. Bye-bye.